put up reminders before lab then. So there's a couple different definitions of an acid and a base. In general, they all kind of have the same effect on the pH or the scale of acidity to basicity in a solution. An Arrhenius acid or base is something that makes hydronium in solution. And what hydronium is hydronium is just H3O plus. So when you put acid in solution, the result is that you get hydronium ions. And so when we talk about a solution being acidic, it's actually related to how much hydronium we have in the solution. And so this is probably the simplest definition of an acid or a base, right? If you put it in a solution and you create hydronium, it's going to be an acid. And so if we had hydrochloric acid, and let's say we had an aqueous version of that, and we add it to water, the way this reaction works is the proton from the hydrochloric acid gets donated to the water molecule, and you're left with a chlorine ion. Right, so this should kind of start to look and feel similar to the ionic compounds that we were talking about in solutions, in that they start to dissociate. The proton dissociates from the chlorine the same way in ionic compounds, sodium and chloride, or chlorine, dissociate from each other as well. And we'll talk a little bit about, how is this related to the strength of an acid and how that's similar to the strength or not the strength of an electrolyte. And so you might also see this written a lot with the H2O on top of the reaction arrow. That's not very important. But instead of writing hydronium, a lot of times you'll just see H+, right? Because really that's the only difference in the solution, is that you just added a free proton without an electron around it to the solution. So you'll see this interchangeably a lot. Hydronium, H3O+, or just the H+ ion. Are there any questions on that? All right, so this is the Arrhenius definition of an acid. The Arrhenius definition of a base, does anyone have any idea what the, oh yeah, I'll go back. You're good. If I'm moving a little fast, actually, I don't have to move too fast. I can just lecture into lab a little bit since we're not moving rooms. I think it's a relatively short lab today, at least just by looking at it, it seems like a relatively short lab, so. Okay, so an Arrhenius base is the opposite, and so an Arrhenius base is something that's going to make, does anyone have an idea what it'll make in solution? Or does anyone remember if they've taken a chemistry class before? It's going to, instead of donating a proton to solution, it's going to be taking one from the solution or directly making hydroxide. The hydroxide ion in solution. So this is OH minus. Right, so we've dealt with a little bit in this class whenever we've used sodium hydroxide, for example, that is a base. We have sodium hydroxide, and we put it in water. Then we get, actually I don't need to put the OH minus there. We put it in water, we get a sodium ion plus a hydroxide ion. Aqueous. Whenever you see the AQ next to the compound in the chemical equation, that just means that it's aqueous. It's dissolved in water. So we talked about how solvation works, and we had the water molecules that surround the ions. That's exactly what's going on here. We just have aqueous version of the hydroxide ion. If we have something that is maybe, so sodium hydroxide, for example, is what we would call a strong base, and I'll talk a little bit about what that means in a second. But if we have something that's a weak base, like ammonia, NH3, and we put that in water, we can also have something where we create hydroxide by taking a proton from the water molecule, right? So here, what has happened is one of the protons from the water molecule has been taken by the ammonia molecule to create the ammonium ion. And then in the end result, we've created a hydroxide ion. So by the Arrhenius definition of an acid or a base, this would be considered a base. And there are three kind of main definitions of acids and bases that you'll see. We're really only going to talk about two because it's not terribly important for us. I'll mention one that we're not going to use a whole lot, but it might become important later when we talk about organic chemistry. But the Arrhenius definition is considered usually the broadest, most basic definition, and it doesn't include a lot of compounds that actually tend to be acidic or basic. Okay, am I good to go to the next slide? All right. And so we also have Bronsted-Lowry acids and bases. In Bronsted-Lowry, the definition basically has to do with the donation or accepting of a proton, right? So an acid is a proton. Oops, I don't have my divider there. An acid is a proton donor, and a base is a proton acceptor. Right. So according to the Bronsted-Lowry definition, it isn't just if we create H3O plus or OH minus in solution. It's are we donating a proton or are we accepting a proton? And so if we think about an acid like hydrochloric acid plus H2O, we see that we get H3O plus, the same as what we had on the previous slide, plus Cl minus. Those are both aqueous, that's a liquid, and that's aqueous like that. And so, again, the proton from the hydrochloric acid was donated to the water molecule. And so in this case, this means that we usually have acid-base pairs that work together. So this is the Bronsted-Lowry acid, and the water in this case acts as the Bronsted-Lowry base because it's accepting a proton from the hydrochloric acid. And then if we think about the ammonia example that we had on the previous slide, we have NH4 plus OH minus. And that's liquid. We see in this case, the ammonia acts as a Bronsted-Lowry base because it's accepted a proton from the water molecule to then become a protonated ammonium ion. And in this case, the water has acted as a Bronsted-Lowry acid because it's donated a proton to the ammonia molecule to become OH minus. So now this is a Bronsted-Lowry acid. And this raises, an important point that water in these solutions can act as both an acid or a base depending on the definition that you're using. And this kind of ability of water to act as an acid and a base in these solutions kind of gives us the medium point for what will ultimately decide how strong or weak in terms of acidity or basicity the solution is, right? So we've heard of the pH scale, and it's water's behavior to act as both an acid and a base that gives rise to the pH scale. So this is kind of like the baseline for how we determine the scale from this point. Any questions on that? Israel?
Do acids have different rules, naming rules when it comes to their stuff?
Yeah, so basically with an acid, hydrogen chloride is how we would name the covalent compound, HCl, right? I'm not going to test you guys on naming acids and bases, but hydrogen chloride is HCl, right? When it's an acid or in the aqueous form, you just replace the hydrogen with hydro, and chloride becomes chloric, and you just put acid at the end of it. So because hydrochloric acid. So that's why when we see each HCl in the lab, I always call it hydrochloric acid. And usually acids are going to have that IC ending, which is ic and then acid. And that's usually, if you ever see that, that means you're dealing with an acid. With the base, it can be a little bit more complicated because you can have carboxylates or different types of negatively charged ions, and they tend to not have just a traditional naming convention the way that acids do. But once we get into carboxylic acids, an organic naming that's going to have an oic ending because it has it has oxygen part of the molecule, and then IC, and then acid ended to it. But yeah, that's a good question.
Does it ever end in ATE too, doesn't it?
Yeah, so like carboxylate will act as a base, right? But it's negatively charged, and so that acts as a proton acceptor. So that's why it's defined as a base in that regard. And so, acid and base is one of those things. The first time you look at it, it's like, okay, that seems straightforward enough. But then if you really kind of sit and think with it, you realize that everything based off of your frame of reference can look like an acid or a base. So you put acetic acid in solution, it donates its proton, for example. It's acidic, that makes sense, right? But now that you have the acetate ion in the solution, well, that ion acts basic, right? Because it's negatively charged. And that kind of leads it directly into what the next slide, what we're going to be talking about, is that in this Bronsted-Lowry definition, any pair of molecular ions that can be interconverted, so when you go from having a proton to losing its proton, they're called conjugate acid-base pairs. All right, so they're conjugate acid-base pairs. And this is like a really big field of study in chemistry, and it's important for a lot of experiments that you do. It's important for, what we'll talk about today and what you'll see in lab, but different buffers work, right? And so buffers are going to work by resisting a change in pH. But these acid-base pairs means you're kind of constantly going between the protonated version and the deprotonated version. And so if you go on to take chemistry, Chem 1A, Chem 1B here at LVCC, Chem 1B, you spend a good, I'd say almost like a month and a half on just weak acids and weak bases, right? So we're kind of skimming the surface of really all the information that's here. And so if we have H3COOH, this is an acid that you guys have seen before. It's called acetic acid. This is what the chemical formula is. So it's an aqueous molecule, and we put it in solution of water. We will get H3OO minus aqueous plus H3O plus. And so unlike hydrochloric acid, this is a reaction that'll go back and forth. And we can see on the left-hand side of the equation that this acts as a Bronsted-Lowry acid. But if we were to flip the equation around, this would act as a Bronsted-Lowry base. And so acetic acid is the Bronsted-Lowry acid. And the way we define the acetate ion here, so this is called acetate, this is going to be the conjugate base. So when we have, in this case, this is going to be a weak acid. When we have a weak acid that donates a proton, the ion that's left over acts slightly basic. Why? Because this ion wants to pull protons off of stuff. It's negatively charged. It wants to pull protons and neutralize itself. And if we look at ammonia, again, I know I keep using this example, so hopefully you guys end up getting tired of it because you know it so well. Ammonia becomes the ammonium ion plus OH minus. And we see here, this acts like a Bronsted-Lowry base. And then on this side of the equation, it looks like something that will donate a proton. So this would be a Bronsted-Lowry acid. And so how we define that is this is the conjugate, let me write that neater, the conjugate base of, the conjugate acid, the conjugate acid of the Bronsted-Lowry base. So with each of these Bronsted-Lowry definitions of acids and bases, when it donates or accepts a proton, what's left over is defined as the opposite, the conjugate of the opposite, right? So Bronsted-Lowry acid becomes a conjugate base, right? That acetic acid turns into acetate, which is the conjugate base of acetic acid. The Bronsted-Lowry base, when it accepts a proton, becomes a Bronsted-Lowry acid, and we call that the conjugate acid of ammonia. So ammonia is the base, and its conjugate acid is the ammonium ion. And really, in the Bronsted-Lowry definition, all you're looking for is the movement of the proton in these cases. Is it accepting a proton, or is it donating a proton? All right, so here we kind of have the reverse reaction of a conjugate acid base pair. So starting from the left-hand side, the product side, or the reactant side of the equation, see if you can identify what's acting like the acid and what's acting like the base, and what's the conjugate acid and what's the conjugate base, right? So in the Bronsted-Lowry definition, we have a base and an acid working together. One's donating a proton, one's accepting a proton. And then we have Bronsted-Lowry base, the Bronsted-Lowry acid, and then a conjugate acid and a conjugate base, respectively. So what's acting as the acid here? H2O, right? The water's acting as acid. Why? Because we see here we have 2 protons, and then here the OH minus ion that's left over only has 1. Let me use red for this because in my mind acids are red. Right, so this starts with 2 and it loses a proton, and it donates the proton to the chlorine ion here, right? That's where one of the protons goes. And that means that this is going to be the Bronsted-Lowry acid. And so then how would we define the OH minus on the product side of the equation here? It would be the conjugate base for the acid. That's correct, right? Because it's left over. We know OH minus, that's the definition, one of the definitions for what a base is, right? So the hydroxide ion. So we know that that's going to act basic, and it's what accepted the, or donated, it will accept a proton if the reaction is going in the reverse way. So that's going to act basic. And then how does chlorine act here? How would we see how chlorine acts? It acts as a Bronsted-Lowry base because it's accepting a proton from the H2O, right? This accepts a proton to then become hydrochloric acid. And we know hydrochloric acid is an acid. And in this particular example, how do we define that acid here? This would be the conjugate acid of the chlorine ion. In reality, this type of reaction, what have we drawn here, doesn't really happen in this way because the chlorine ion is not basic, but it still highlights how we have something that acts as an acid and something that acts as a base together based off the movement of a proton because of the Bronsted-Lowry definition. And then what's left over is the conjugate of whatever the definition was, right? So the chlorine ion is the Bronsted-Lowry base, and the resulting molecule from that is hydrochloric acid. That's the conjugate acid for the Bronsted-Lowry base here. Okay. Any questions on that? No? Huh? All right. Well, good thing I have another example for you right here, right? So remember, when we're doing this, we're looking at the movement of a proton, of the proton in this chemical equation. Both of these molecules look like. So you don't have to know what these molecules look like just yet. I'm just showing them to you because we will be drawing stuff like this in the next couple weeks, kind of familiarize yourself with them. All right, so what is acting as the Bronsted-Lowry acid and what's acting as the Bronsted-Lowry base here? Yeah, that's acting as what? The acid, right? The Bronsted-Lowry acid. Why? Because it starts with a proton, and you see on the left-hand side it loses its proton, or on the right-hand side it loses its proton. So that means it was the proton donor in this reaction. So that's the Bronsted-Lowry acid, and that means what's left over is what? What kind of base? Conjugate base, right? This is the conjugate base. And then we know whatever the other molecule is here is going to be acting as what? The Bronsted-Lowry base. And then what's left over is the conjugate acid. And on the pictures that I've drawn here, like I said, you guys don't know how to have to have any idea what these structures look like. Remember I talked about Lewis structures kind of not going away, and to move forward, it's good to have a good understanding of those. So these right here are both of the Lewis structures for these organic molecules, and these are both called alcohols. And then we have a simpler representation where we ignore drawing a lot of the explicit elements, but represent them by either kinks or endings of lines and stuff. And we'll talk a lot about this once we start getting into organic chemistry. But this is kind of where we're going to be moving towards in the future. So if you have any issues with Lewis structures and stuff, remind me at the end of class if you want the direct link, but I'll probably post something today. I was just became aware there's a workshop tomorrow, I think, in one of the study centers that's going to be going over molecular shape, which isn't going to go away, intermolecular forces, which isn't going to go away, and then Lewis structures, which will help you understand as we get to more complicated molecules like these. Ethan? Yeah, so that exactly. So the way the chemical reaction, is written is how you will define the Bronsted-Lowry acid or base. I could write this chemical equation backwards, going the opposite way, and you would define, the conjugate base as the Bronsted-Lowry base, and the conjugate acid as the Bronsted-Lowry acid, and then yeah, you're starting from the left side. What's doing the donating? What's doing the accepting from the left side? And then going to the right side. Yeah. So that's how you're going to be observing these. Because in reality, what's happening in solution is both reactions are happening. Usually one reaction is more favored, the forward reaction, and the reverse reaction is happening less. Right? And so we'll talk a little bit about what that means in terms of equilibrium in a little bit. Good question. Okay. All right, so here we have a different type of example. We'll go through this. I have lots of examples here, but we're probably gonna save a lot of them for next Tuesday, because I kind of just want to get through the definitions so you guys can understand a little bit about what's going on in the lab. But it says, write the formula for the conjugate acid for each of the bases shown below, right? So here where I'm told that you're told that all of these are the Bronsted-Lowry bases. And you're going to be writing the formula for the conjugate acid. Right. Here we have HS minus, and so when this, I'll write how it reacts with water once, and the other ones it's just going to be implied in these cases. So these are all bases. So here we have plus H2O, and then we know a base acts by creating what in solution, according to the Arrhenius definition? A base. How does a base? So it will create something that's acidic because it creates its conjugate acid according to the Bronsted-Lowry definition, which means that it's going to do what with respect to this water molecule? Yeah, it creates hydroxide according to the Arrhenius definition, and so it's going to take a proton from the water molecule And so we get H2S, right? And neutralizes it because we're adding a proton. So that's a positively charged proton to it. It's going to neutralize that. And then what's going to be left over is OH minus, right? So two things kind of reassure us that we're in the right direction here. We know it's basic, so it's creating OH minus in solution. And then it's also creating a conjugate acid in accordance with the definition of the Bronsted-Lowry conjugate acid-base pairs, right? So this would be the answer, you know, that you wouldn't need to write out this whole chemical equation to answer this question. I was just doing this once to highlight how this works, right? The proton gets donated from the water molecule to then create H2S, which is sulfurous acid, in the solution. All right, so we accepted a proton. All right, what about ammonia here? What's the conjugate acid for that? NH4 plus, right? So this goes to NH4 plus. Because it accepts a proton from water, because it's acting as a base, we've added a proton to the neutral molecule, so that's why it becomes positively charged here. It would still create OH minus in solution, right? Because it would be taking it from the water molecule. I didn't write the whole chemical equation again, but that's exactly how it works in solution. And then the last one, we have carbonate, and then it's gonna go to bicarbonate is gonna be the next ion. So what is this gonna look like after it accepts a proton because it's a base? So it's not going to be CO4, right? Because the oxygen doesn't change. It's just the proton that changes. So it'd be HCO3, right? HCO3, 1 minus, right? Because you've added one proton, which is positive charge of 1. So then the total charge goes from 2 minus to 1 minus because we've added a positive charge. So these would be the conjugate acids for each of these chemical formulas. Because in acids, usually H always, it doesn't always go in the beginning, and if you put it at the end, that would be fine. This is how the molecule will be written when you see it, though. Usually when we think about metals and ionic compounds, right, what usually goes in the front? An ionic compound, like sodium chloride, let's use that as an example. The metal goes in first, right? So in this case, since the proton acts as a, something that dissociates from the molecule, like a metal, and it's positively charged, that's usually why you see it in the beginning. But if you put it at the end, I wouldn't, mark you down for that. Okay. And since I think this is probably useful to go over one more example. So here we have a bunch of Bronsted-Lowry acids. And then you're gonna write the conjugate base for each of these. And so this question that Geeta just had about how do you know it goes in the front or at the end, that is somewhat relevant here because you have to think about which proton is being donated to the water, right? So if we look here in what is this gonna be? This would be methanol, or methanol. We see that we have an OH and H3. In general, the protons that are gonna be donated from these organic molecules are always gonna be protons that are attached to an oxygen here, right? And the reasoning for that is because oxygen is a very electronegative element compared to hydrogen, so it's easy for the oxygen to kind of absorb those electrons and then let the free proton go. That's not super important for this question, but for the second one, it is somewhat relevant because of the fact that there's multiple protons on this molecule. Lowry acids work by doing what? Donating a proton, right? And so this first example, we have hydroiodic acid, right? So you're asking, how do we know it's an acid? Well, hydro because it's a hydrogen-based acid, and then iodic because iodo turns to iodic, and then you just add acid for it. Like I said, I'm not going to be testing you guys on how to name acids, but that's how we name that acid. So what is the conjugate base for this acid? It would just be I minus, right? Because the iodine, if I write out the full chemical equation for this, means it's being put in water, and then it's going to create H3O plus and I minus, right? We have the same charge on the left-hand side of the equation as we do on the right-hand side. And this proton gets donated to the water molecule to then create H3O plus. And what's left over is I minus, and I minus is what in this case? The conjugate base, right? The conjugate base. Okay, so that's what it is for the first one, iodic acid, hydroiodic acid. What about for methanol? What's the conjugate base going to be?
CH3 negative.
Yep, CH3O minus. Right? So like I said, this is somewhat relevant which protons being donated in this case. And in hydrogen or oxygen-based acids, it's always going to be one that's attached to an oxygen, right? And so the fact that this is written CH3OH instead of CH4O tells you that this proton is on an oxygen. So a lot of times that's the indicator for that. We'll talk more about that when we get to organic molecules, but that's a general rule when we're dealing with acids and bases, right? The H that's attached to the hydrogen, or the oxygen, I mean, is going to be the one that's going to be donated. And then this is the conjugate base. And then for the last one, which is nitric acid, what is the conjugate base for that? NO3, 3 minus, right? Because you're losing a proton, which is a positive charge, so it becomes NO3 minus. Okay. All right, so how do you guys feel about that? Thumbs up, side, thumbs down, conjugate acid, base pairs. Okay, so we'll get more practice on that, next week, and I'll make sure I'll give you guys a problem set on this because there are also problems dealing with calculation of pH and stuff that we're not gonna have a lot of time to go through today. But we'll go through all of the theory and whatnot today so you understand what's going on in the lab. And then next week we'll go through the first hour on Tuesday, kind of how to solve. I'll give you guys a lot more examples of these. All right, so the way that the general idea is that whatever's on the left-hand side of a chemical equation is either acting as Bronsted-Lowry acid or base based off of if it donates a proton or if it accepts a proton. In most of these cases, if I say this is acting as an acid, that means it's going to donate a proton. So the conjugate base should have one less proton. If I say it's acting as a base, then it's going to accept a proton. The conjugate acid should have one extra proton. And when I say proton, I'm using that with hydrogen interchangeably, right? Because what's going back and forth isn't the electron also that's associated with the proton, it's just the proton itself, right? The negatively charged electron stays with the conjugate base in these cases. Or it stays with the conjugate base or the Bronsted-Lowry base. Okay. Are there any questions? So I know I saw some thumbs down, thumbs to the side or whatever. Are there any questions that I can answer about that to kind of clear things up a little bit? I know we're just going over this for the first time, so I don't expect you to understand it 100% right now, but if there's any questions that pop up, right? The earlier we ask a question, the faster I can help you understand what it is that's confusing. No immediate questions? Okay. All right, so that kind of leads into something that I've been alluding to, but I haven't necessarily said all right. It leads to strong acids or weak acids, acid or base strength. And so strong acids are going to be, and again, acids are red in my head, are going to be those that dissociate 100% in solution. And so what that means is that when we put, for example, hydrochloric acid, which is a strong acid in water, 100% of it will turn into Cl minus and H3O plus. Or you could just put H plus. You'll see that interchangeably written like this. right? So 100% of it. That means every single hydrochloric acid molecule turns and dissociates into a chlorine ion and hydronium ion. So that's the definition of a strong acid, right? And it's a strong acid because what ultimately leads to whether a solution is acidic or basic is the concentration of that H3O+. And so this might look a little bit familiar. I know we only touched on it briefly last week, but so strong acids and bases are the same as strong. Does anyone know what else we talked about that dissociates completely in solution? Like when we were talking about solutions last week, it was towards the end, we were talking about, I hear, but sorry, I heard a bunch of like whispers, I couldn't really tell what it was. So it's ions, right? And what were those called when they dissociate into solution, right? Salts. So a salt is a specific type of, the word I'm looking for is electrolyte, right? Electrolytes are something that conduct electricity in solution, but that was when we put an ionic compound in solution. It was a strong electrolyte when it dissociated completely into its two ionic components, right? So sodium chloride, strong electrolyte, because when you put it in solution, 100% of the time it dissociates into sodium positive and chlorine minus, right? So these are the same as strong electrolytes. And its acids and bases work essentially the same way, except it's the proton that's dissociating and not the a metal dissociating in an ionic compound. And color's almost done. I'll fix it later. Okay. And so with bases, it's the exact same thing with a base. For example, with a sodium hydroxide, which earlier I said is a strong base. Usually, strong bases are going to be associated with a metal because they form a hydroxide ion is a negatively charged ion. It will have sodium hydroxide, and maybe it's solid. You dissolve that in water, and 100% will dissociate into sodium plus and OH minus. Right, so the hydroxide ion in a strong base is oftentimes already in ionic form with a metal for strong bases. So the difference between a strong acid and a strong base a lot of the time is the strong acids tend to be covalent compounds that donate a proton to water. Strong bases tend to be ionic compounds that donate a hydroxide ion to the solution. Earlier when I showed ammonia, ammonia is considered a weak base. Even though it's a proton acceptor, it's considered a weak base because of that. And I'll talk in a second about what a weak base is. Right, so strong bases tend to be ionic compounds, and then strong acids are covalent compounds. And that's just true for acids in general. Acids in general are going to be covalent compounds. Any questions on that? And so a weak acid or weak base are those that only ionize partially in water. And these are considered weak electrolytes. It's the same thing as a weak electrolyte. And so, for example, if we have acetic acid is considered a weak acid. What this means is that we have a reaction that goes both ways. OO minus aqueous plus OH minus. Oops, sorry, H3O plus. Right, so this reaction does not happen 100% of the time. That means that, you know, we might have something, for example, like 70% this in solution and 30% acetate in solution for acetic acid, for example. Right, so not all of it gets converted into its conjugate base. And that's because it's a weak acid. And it's the same thing for a weak base. So ammonia, for example, we put it in water and we get the ammonium ion and OH minus, and we might have 70% of this in solution and 30% of the ammonium ion in solution. And you notice that for both of these, put it here, I put a star here and a star here, the reactions go in both directions. And I'll talk more about what this means in terms of equilibrium, but basically the forward reaction is happening and the reverse reaction is happening. So you're constantly exchanging between ammonium and ammonia, between acetate and acetic acid. Yeah, strong acids and bases are only in one direction. You do not have the reverse acid at all. That's why when we did the first example of the conjugate acid-base pair, it used H2O plus Cl minus. A chlorine ion is not going to pull a hydrogen from a water molecule ever in solution. And so these also, strong acids and strong or weak acids slash bases are covalent molecules. Because the way, with a strong base, I said it directly donates a hydroxide ion to solution. Weak bases, the way they work is always by accepting a proton. And weak acids always work by donating a proton. Okay. Am I good to go on to the next slide? No, I'll wait out a little bit. While people are still writing, are there any questions for acids and bases? No immediate questions? Okay. And the next slide is just a kind of pictorial representation of what this looks like. I know when I write a lot of these chemical equations, they take a second to actually write down because, we have to look up constantly. I've written these, both of these equations probably 1,000 times just in the last couple months, so that's why I can write these down very fast. All right, is everyone good? All right. So this, pulling of a hydrogen or donating of a hydroxide ion, basically is an ionization of water molecules is what we're looking at. We're either protonating a water molecule or deprotonating it or directly donating hydroxide ion to solution. So for strong acids, again, this means that all of it, when you have the representation for a acid usually is HA, right? Because we're always donating protons. So whenever you see HA, this just means a generic acid. And whether it's strong or weak, I would have to tell you, HA represents a generic acid. For, in this example, this is a strong acid on the left-hand side. And we see if we start off with HA, we end up with 100% of it being converted into H3O plus and A minus, right? So we have a 1-to-1 ratio. Every HA gets 1 H3O plus and 1 A minus, which is its conjugate base here, right? So this is A minus, which is the generic conjugate. I'm just gonna put CONJ base. And if we have a weak acid or weak base, we see that we start off with a certain amount of our weak acid in this case, but after we've put it in water, there's still a good amount of the weak acid present and only a little bit of HA and A minus, right? So that means that at equilibrium, when the solution is no longer changing, the acid, the weak acid, has not donated all of its protons, right? And that's what we meant when we said it only dissociates partially. The Bronsted acid only donates its proton sometimes to the water molecules to create H3O plus in solution. All right, so this is just a pictorial representation of the concentrations, right? H3O plus is what makes the solution acidic. When we add the HA to water in a strong acid, all of the HA gets converted into H3O plus and A minus. In a weak acid, only partially, part of what we started with gets converted into H3O plus and A minus. And then it's the exact same thing for bases. I don't have a pictorial representation for bases, but we start off with HB that gets protonated, and we can go into that more, but I'm not that worried about it. This is just important to understand that with weak acids and weak bases, they only ionize partially when we put them in a water solution. Strong acids, strong bases, ionize 100% of the time. Okay, am I good to go on to the next? Right, so some examples that you'll see for strong acids and weak acids, hydrochloric acids, all of the basically halogenated, or the protonated halogens in aqueous form are strong acids. It's very easy for them to donate their proton. Why? Because they're relatively electronegative. And so it's easy for them to kind of take all the electrons from the proton and lose it. Nitric acid and sulfuric acid are also strong acids. Those protons are easy to dissociate. It has to do with the number of oxygens in the conjugate base. The more oxygens you have, generally the more acidic the molecule is going to be. And then weak acids, something like acetic acid, carbonic acid, which is the acid and buffer that you have in your blood, phosphoric acid. Hydrofluoric acid is considered a weak acid because it's so small and electronegative that it doesn't, fluorine ions will not pull hydrogens in solution or donate its proton in solution. Hydrocyanic acid and hydrosulfuric acid. So those are some examples of weak acids and weak bases. So generally, I don't care if you memorize what's a weak acid or a strong acid. The only ones that I would say you should know would be something like hydrochloric acid, nitric acid, and maybe sulfuric acid too. So those are good ones to remember, that those are strong acids, right? The weak acids, I will usually tell you that this is a weak acid if you're ever given a problem related to that. Okay. And then here we have strong bases and some weak bases. And so like I said, most of the strong bases are going to be ionic compounds. And what do you notice about all of these strong bases? What's a common theme you see with all of the strong bases? I guess there's a couple common things, but what do you guys notice about the chemical formula for all of them? They always have the OH associated with them, right? So they all have OH minus because when they dissociate in solution, they directly donate the hydroxide ion into solution. They all have OH minus, and what's another thing? Does anyone notice anything else? Say that again? Yeah, they're all of these are either group 1 or group 2. These are all going to be metals, right? So that's how we know that they're all usually ionic compounds, right? So these are all metals, which just reinforces the idea that all of these are ionic compounds, right? And so strong bases are always going to be ionic compounds. They work by directly putting hydroxide into the solution. And then the weak bases, these are going to be covalent molecules. So we have something like urea, and also ammonia, which is the only one that I would want you to remember. This is a weak base, right? And I've used that example a lot. It's an easy one to understand how the protons move for a weak base in solution, right? So ammonia is a weak base. Okay. Are you guys good to go on to the next slide for this one? Okay, and so before we move on and continue with acid and base, I just want to take a second to discuss a little bit about equilibrium. So when we're talking about equilibrium, when we talk about solutions, we talk about concentrations of solutions. How we represent the concentration of a compound is usually by brackets, right? So this means the concentration of, right? So for example, if we had something like H3O plus with the brackets around it, this means the concentration of H3O plus in the solution. And so an example of what that would look like in a problem, if you had something written like H3O plus equals 2 molar, right? So this is usually going to be used in molar amounts, or the concentrations that are going to be used when we're dealing with acids and bases. I'd say very rarely do you ever see it in mass to volume percent, or mass to mass percent, or volume to volume percent. And so I just want to say that right now, like when we're dealing with things in equilibrium and acids and bases, these brackets are used to represent the concentration. And the reason that we use kind of the shorthand notation is because things like the pH of a solution, or how acidic or basic something is going to depend on the concentration of, for example, the hydronium ion in solution. And so this is just something that's important for understanding equilibrium. And so equilibrium is when the reaction is still happening in the forward and reverse directions, but the concentrations are not changing anymore, right? So this is when the concentrations stay the same. All right, so you can think of it as you're at a music festival, for example. You have people outside the gate, people inside the gate, and if they're letting the same amount of people, or the same ratio of people go inside and outside, the total number of people outside and inside is not changing, even though people are constantly moving back and forth in and out of the festival. So that's the exact same idea with equilibrium, is that we have a reaction that's happening in the forward direction and the reverse direction. And so that's indicated by the forward reverse harpoons here, is what they look like in a chemical reaction, right? This is saying that we have a forward rate and a backwards rate for the reaction. And so to put a numerical value to the ratio of these concentrations at equilibrium, we have something called the equilibrium constant. And that puts a numerical value to the ratio of concentrations of the reactants and the products at equilibrium. Question? So the concentration doesn't change, right? Because things are happening forward and things are happening in the reverse, and they're happening at a rate at which the amount of reactants and the amount of products stays the same. So the overall amount of both sides stay the same, even though people are still moving back and across, or the molecules are still moving back and forth across the reaction arrow. But the amount that's there, it stays the same, right? Because nothing in real life is ever static, perfectly still, So especially at the atomic scale, everything, reaction constantly happening back and forth. Things like thermodynamics and entropy and everything cause things to be constantly in motion, but the concentrations stay the same, right? So if we, at the atomic level, we see these reactions are still happening, but when we take a step back and look how much is there on the reactant side, on the product side, like the big picture, the concentrations are staying the same. And so how we represent this equilibrium constant, right? This equilibrium constant is usually represented by uppercase K. So if we have a general reaction, A plus B goes back and forth to C plus D, then K is equal to the concentration of the products over the concentration of the reactants, and that's equal to C times D over A, concentration of A times the concentration of B. All right, so A, B, C, and D, that can be any molecules or any chemical, any molecules that are involved in a chemical reaction. And so I'll write an example on the next slide. The only thing that we can add to this, and in acids and bases, it's usually not very important, because in acids and bases, everything usually happens into a 1-to-1 molar ratio. One hydrochloric acid creates 1 mole of hydronium and 1 mole of conjugate base, right? And so the only thing that you can see, and you might see, so this is the important part, but you might see if there's each of the lowercase letters here, those represent the molar coefficients, right? The stoichiometric coefficients. How those show up in the equilibrium or constant is that they're just raised to the power of those. Right, so you have the concentration raised to that power. And like I said, in acids and bases, and in equilibrium in general, I'm not going to be testing you guys on any of this. It's just to give you a little insight as to how the pH and stuff is going to be defined, is using this language a little bit. And how you get this expression, we're not worried about how we actually get it. I'm just telling you guys this is what the equilibrium constant is. And what is this? This is just the ratio of the products over the reactants. And so at equilibrium, this ratio is always going to stay the same. The system always wants to reach this ratio again. So if we increase the reactants, the reaction will then shift to make more products and stuff. And so if we increase the product, so remember when we talked about kind of movement across the membrane, we're talking about, if we increase concentration outside of the membrane, stuff will want to move inside to make the concentration equal. It's the exact same idea here. It's the same law of mass action, except instead of across the membrane, we're moving across a chemical reaction arrow, right? If we add more products, the reaction is going to make more reactants so that the ratio stays the same. If we add more reactants, the system will make more products so that the ratio stays the same. This is kind of the idea of what equilibrium means. We're always trying to reach this equilibrium ratio. Okay, and so like I said, I'm not going to explicitly test you guys on writing equilibrium constants, but it's important for understanding the where pH kind of come from. And so another thing I'll note about the equilibrium constant is only aqueous and gas molecules are included. So if you ever see any other physical states, like liquid or solid, those are never included in the equilibrium constant. The explanation for that is a little complicated, but really equilibrium is only affected by aqueous molecules, which in acids and bases is important, and gaseous molecules, which in chemical reactions involving gases is important, but we're not going to be talking about gases a whole lot in this class. Okay, am I good to go on to the next slide? All right, I know I'm kind of going over a little bit. We'll take a decent break. Let's see, we have 2, 3, 4, 5. All right, so 5 more slides. Okay. And so now we're going to start talking about, okay, so where does this scale, this pH scale, come from? Well, we saw earlier that water can act as both an acid or a base in solution. So that means if we just have a little bit of water, and that's the only thing that we have in solution, well, then we can have 2 water molecules that interact with each other. And one acts as an acid, and the other one acts as a base. So we get H3O plus, aqueous plus OH minus, right? So one of the protons, let's say this one, actually I'll use the other molecule. One of these protons gets absorbed by one molecule, so that acts as the Bronsted-Lowry acid or base. Right? If it accepts a proton, what does it act as? Bronsted-Lowry acid or base? It should be the base, right? Because if we accept protons, we're bases, and if we donate protons, we're Bronsted-Lowry acid. And so this can just happen in neutral water, right? So even though water is, we all know water is neutral, pH of 7, we've heard that, a lot in our lives before. There's still OH minus and H3O plus present. And so that means that there is some standard value for what the equilibrium constant should be here. And so that's called Kw. This is the ion product constant, is what it's called. And it is going to be equal to the concentration of H3O plus times the concentration of OH minus. And this is where, the fact that the equilibrium constant doesn't include anything that's liquid in its expression, right? It's a concentration of the products over the reactants. So the products are these ones, reactants are here, but both of these are liquids. So we don't, liquid molecules are not aqueous molecules, so we don't include them in the expression for equilibrium. So this one is basically just all, these concentrations are just over 1 because they're not included in the expression. And so this gives a ratio of how much H3O plus and OH minus is in a neutral solution, right? So this is where we kind of set the baseline for, how do we know where H3O plus and OH minus is, when we're defining how acidic something is. And so all aqueous solutions then have H3O plus and OH minus, and an increase in one of them basically moves that the solution, right, to decrease the concentration in the other, right? So you can always, if you know what the OH minus concentration is in solution, then you know what the concentration of H0 plus is based off of the previous relationship. And so this, ion product constant that we get from how much OH minus and H0 plus is present in neutral water gives you this relationship between them. And so the experimental value at room temperature is 1.0 times 10 to the 4. That's equal to Kw, which is equal to H3O plus times OH minus, the concentration of both of these things. And so you don't have to know where that comes from, but that's where we get our kind of baseline for what the concentration of both of these are in a neutral solution. And what this, second bullet point is saying here is that if we change the concentration, let's say we add a strong base to solution, that means that we add OH minus here. That means that the amount of H3O plus is going to be adjusted to keep this constant the same, right? So that was the idea with equilibrium, that if we change one of these concentrations, on the reactant or product side, the reaction will shift in a way so that the ratio stays the same. So this ratio here is represented by this number. And if we change one of these concentrations, the other one will shift so that this ratio stays the same. Right? The only thing that's different from what I showed here is that, the concentration of the reactants isn't showing up at all because we can't have anything that is not in a gas or aqueous form in our expression for the equilibrium constant. And so that's why we don't have anything in the denominator here for this ratio, but it's still the same idea. If we add one of these, the other one is going to shift to make sure that this ratio or this concentration stays the same. And so when the concentration of H3O plus is greater than OH minus in a solution, then it's considered an acidic solution. Okay, I'll go back. I'll continue this in a second. And then we have let me see, 1, 2, 3, 4. The next two slides go quick, and then I'll describe what pH is, and then after that we'll take a 15-minute break or so, and then we'll start lab after that. Okay, so the way we define if a solution is acidic, remember I alluded to this before, is that when the concentration, right, those brackets mean concentration, is greater than, of H2O plus is greater than the concentration of OH minus in solution. So that means that the solution is going to be acidic. And so if we have a concentration of 1.04 times 10 to the minus 4 molar, we know that this ratio of equilibrium wants to stay the same. Let me write this in general. We have H3O plus, OH minus. We know that this ratio wants to stay constant, and that wants to stay equal to 1.0 times 10 to the minus 14. Right, we know that this ratio wants to stay at that value. And then we're given the concentration of H3O plus times 10 to the minus 4 molar. Then what should happen is the amount of OH minus should be adjusted so that we still have a total ion product constant, or the ratio of these products at equilibrium, such that their multiplication of both of these gives us 10 to the minus 14. And so if we were to solve then for OH minus, we divide both sides by times 10 to the minus 4, 1.0 times 10 to the minus 4. We can just use ideas of scientific notation. That'll give us 1.0 times 10 to the minus 10, because this will cancel out on that side, is equal to the OH minus concentration. So this would be 1.0 times 10 to the minus 10 molar. Right, so in an acidic solution, what that means is if we pay attention to the exponents of both of these, right, it's a larger negative exponent, which means that the amount of H3O plus is a lot larger than the amount of OH minus. Right, so does that make sense? If we have an acidic solution, the amount of hydronium, which is what we create when we put acids into water, is larger than the amount of OH minus. And the amount of OH minus shifts so that the ratio of OH minus and H3O plus stays the same. All right, and that's what that KW is. And so then you can imagine if we have a basic solution, that is going to be the opposite, where you should have less H3O plus than OH minus in solution. So when the OH minus is greater than do you need me to go back, Jonathan? Right, so the opposite should be true in a basic solution. Good? All right, is everyone else good? All right, so the opposite should be true in a basic solution. So if we have 1.0 times 10 to the minus 6 concentration of OH minus, Kw is equal to 1.0 times 10 to the minus 14, which is equal to H3O plus times OH minus. We can divide both sides by the concentration of OH minus. On the right-hand side, that concentration cancels out, and then we can plug in the values. So you get 1.0 times 10 to the minus 14 over OH minus is equal to the concentration of H3O plus, and that is times 10 to the minus 14 divided by 1.0 times 10 to the minus 6. So that should give us 1.0 times 10 to the minus 8 molar. 0 times 10 to the minus 8 molar. And so what we're doing is we're just kind of showing, because of our definition of equilibrium, we're just showing that that first bullet point there is true when a solution is basic, right? That first bullet point is true because we want to keep, again, the ion product constant is a constant value that's true for room temperature water an aqueous solution for no matter what the concentrations of H3O plus and OH minus are. And whenever we increase the concentration of the other, whenever we increase the concentration of one, the other has to be adjusted to keep this value constant. And we see that if we look at the values for a basic solution, right, it's a larger negative number, which means the concentration of H3O plus is smaller, right? For basically 10 to the minus 8 is like 1 over 10 to the 8, so we're dividing by a larger number. So that's a much smaller concentration. And the other thing, in general with acids and bases, usually you're dealing with very, very small concentrations relative to the amount that's of solvent that's present. So the amount of water is much, much larger than the hydrochloric acid or H3O plus or OH minus that's being created in solution. Okay, am I good to go on to the next one? All right. So this then brings up what the pH scale is. And so it's saying what the pH scale is, it's a scale that tells us how acidic or basic a solution is. And so the acidity of a solution is usually measured on the pH scale. We also have one that defines it in terms of basicity, which we're not really going to deal with. That's called the pOH scale. And it ranges from, does anyone know the range for a pH scale? 0 to 14 is usually what the pH scale is. And so that's actually related because if we looked at the Kw value, that value is 10 to the minus 14, right? So that value is what determines the range of this pH scale. And it's saying that at a neutral solution, we should have equal concentrations of H3O plus and OH minus, right? So at neutral, that means that H3O plus should equal the concentration of OH minus. And so if we look at our expression for Kw, and where we get this 1.0 times 10 to the minus 14, that's something that's measured experimentally. This isn't something that you just know by solving equations and stuff. You have to measure that value experimentally. That means that we get H3O plus times OH minus, and if those two things are equal, that's like taking the square root of that value. That has to be equal to 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7. Right, so when those things are equal, that means we add those exponents together, and that's where we get the minus 14 from. Right, so at neutral, the pH scale is defined by this number, and the maximum number that this can reach is going to be minus 14. So that's how we define these scales here, is based off of the concentration of these two quantities. And the pH scale isn't some, formula that tells us about any actual physical quantity. It's the same idea as like with the Richter scale or the scale that determines the magnitude of hurricanes, earthquakes, tornadoes. These are scales to give us a general idea for how strong these forces are. Here we're talking about the general idea for how strongly acidic or how strongly basic a solution is, right? So that's why when you hear about an earthquake scale, they're saying, well, if it's a 4 to a 5, it's not like you just added 1 to how strong the earthquake was. It's by a factor of 10 usually, right? Because if we look at the concentration here, when this changes to 8, and this number is going to be related to what the pH is, that means that we've divided it by another 10. So the fact, whenever we look at the pH going from 1 to 2, that means the concentration of H3O plus in that solution has changed by a factor of 10. And so that's why when we define what the pH is, the pH is just going to be related to the concentration of the H3O plus that's in solution. It's minus the logarithm of the concentration of H3O plus. And you're like, well, where did that come from? What's the logarithm and all that? Well, logarithm is just a mathematical operation And what the logarithm really does is it just tells you about how big this exponent is. Right? So logarithm, we can just think of it as just a mathematical operation that tells us how large this exponent is. And what does that exponent tell us? That exponent tells us what's the concentration of that in solution. It's a lot easier to deal with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 than it is to deal with 1.0 times 10 to the minus 7 or 10 to the minus 8.2, right? So that's why we use the logarithm. It's just a way that we describe the magnitude, right? How large that number is. And we put a negative sign there because the negative sign just cancels out the negative sign that's in the exponent there. So this is how we define the pH of a solution. And you can do the same thing in terms of the OH, right? Instead of H3O plus, you define the POH. So conversely, the POH, which will describe how basic a solution is minus the log of the OH minus concentration, right? So you can say how basic or acidic a solution is either in the pH scale or the OH scale. And they're just gonna have opposite trends to each other. And so, am I good to go on to the next slide? Yeah. So what this means is that at a neutral point, we go between 1 and 14. This is neutral for both and this will be the pH scale, and in blue I'll have the POH scale. On a POH scale, this is going to be basic, and this is going to be acidic, and at a pH scale, 14 is basic, and 1 is going to be acidic. Right, and the reason they're just opposite to each other is because when you increase the other one to keep Kw, the ion product constant, the same, you decrease the other. Alright, so the lower the number is for a pH, the more acidic it is. The higher that number is for a pH, the more basic it is. We're not really going to deal with the POH scale, but you can do everything that we do with the pH scale and the POH scale. That's why I said acids and bases are a little confusing, because you get the definitions, you're like, okay, that makes sense. But really, if you're looking at things from the POH scale or the pH scale, it kind of flips everything around, and kind of, it's the exact same idea, it's just everything gets flipped around. So it's easy to kind of get confused in that. We're only going to be dealing with the pH scale. Okay, so that's how we define the pH scale. And the important thing to remember from this is just, what is the relationship of the pH to the H3O plus concentration. For the Kw, this is the thing we remember from this, because we'll probably go through some problems where you have to use both of these, like a two-step calculation with the pH and concentrations in solutions. Okay, and so the last thing we'll talk about, and then we'll take a 15-minute break, is buffers. And so the basic idea with a buffer, question? This slide? So the basic idea with a buffer is a buffer works by resisting a change in pH. And so in our blood, we have a carbonic acid carbonate buffer system, right? Because you can imagine that in your body, you don't want the pH to change a whole lot, right? You want the pH to remain within some range. And so the way buffers work is they're usually a weak acid and a weak base. And if you add equal amounts to a solution, then if, let's say some other acid, someone injects some hydrochloric acid into your veins, which probably isn't going to feel very good. The way the buffer works is the hydrochloric acid is going to dissociate right away. Instead of letting it create H3O plus, the conjugate base is going to come up and eat that proton, right? And so that means there was no H3O plus made in solution. It didn't let it create H3O plus, so the buffer didn't change, the buffer resisted the change in pH to the solution. And so what this means is that if you were to look at how the pH changes as we added, let's say, milliliters of acid, remember HA was the general term. So the y-axis here is the pH, and the x-axis here is how much acid you're adding. You might see an initial small change in the pH, but then as we add more and more acid, the pH is staying relatively the same, until all of a sudden we've eaten up all of the buffer that's in solution. Then you see a large increase in the pH, and this is where you die. Right? If this is your blood, that's where you die, right? If you add so much acid that your carbonate buffer doesn't work in your blood, then the pH of everything changes. You start getting reactions with your proteins, your cellular membranes start to lyse, and that's not good. So the way the buffer works is it doesn't let it create H3O plus or OH minus in solution. When acid or base is added, it takes that proton and prevents H3O plus from being created, right? So this prevents H3O plus or OH minus being created in solution. And so the main idea, and so today you're going to be looking at the effectiveness of some buffer. You're not going to, so usually what this is called a, if you guys maybe have done this in high school before, a titration curve. And if you go on to Chem 1A or Chem 2, you will do a titration in the lab. This is what that looks like. We're just going to be using pH paper today to kind of look at the how the pH changes. And so I'm going to write a chemical equation on the next slide just to give you an idea of what that is, right? Because I'm saying the buffer eats the the proton so that it doesn't change the pH in solution. But I kind of want to give you an example of in a chemical equation what that looks like. Am I good to go on to the last thing we'll talk about? Mm-hmm.
What's the bottom part again?
This is the milliliter of acid that you're adding, right? Oh, sorry. So this should be, it should be going down in this case, but that's fine. So the pH is basically, as we're adding acid, pH should be going down. So I'll put 14 at the bottom here. 14 and 1 there, right? As we add more, right? As we're increasing the amount of acid that we add, we see the pH is staying the same, right? It doesn't change at all because the buffer is coming in and it's eating all the H3O plus, eating all the protons before it creates H3O plus in solution. Then once all of the buffer is gone, the pH changes drastically because now the H3O plus is directly going into solution. For a strong acid or weak base without a buffer present, when you add pH to the solution, the pH will just start going up right away, right? So the buffer, that's why you've heard terms like a buffer range, and not just in terms of pH. Whenever you're looking at something that you don't want to change as the system is disturbed and whatnot, that's usually called a buffer range. And so buffers have a direct correlation to chemistry when we're talking about acids and bases. Okay, so how a buffer works is, let's say we have acetate, HCO minus in solution, right? Acetate ion. This is our Bronsted-Lowry base because it's a proton acceptor. And you add acid to solution. So acid, strong acid added to solution. What happens is the acetate is going to come and take the extra proton that's on this molecule, and it's going to create H3CO, oops, sorry, I forgot an O on the other side, OH, OH plus H2O, right? And water is neutral. This the H3O plus / H plus proton, and it formed neutral water. All right, so how the buffer works is we have our acetate ion that then interferes with H3O plus being created in solution, to then create water as a byproduct, right? So it neutralizes whatever acid comes in. When the pH starts changing is when when you've used up all of the buffer that's present. Once all of that gets used up, again, that's not good for you and your blood, but in terms of the buffer, that's just when the pH starts to change. Okay, so that's where we're gonna end